So yeah, as mentioned, we'll kind of touch on cybersecurity, performance, and connected vehicles. First of all, though, a quick intro. This is my first AESIN conference, so yeah, just a bit of background. I've been building connected systems for about 20 years, mainly focused on digital identity, cybersecurity, and around 6 years ago moved into the automotive area. I'm CTO and co-founder at Beam Connectivity, and prior to that worked at Dyson, leading the development of a connected vehicle solution for the ill-fated Dyson EV. And we've got a sole focus on building high performance and highly secure connected systems for vehicles. So the three things I'm going to talk about: first of all, a bit about context, a bit about momentum and challenges with connected vehicles. Next, focus on the title of this talk, which is about the performance security trade-offs, and then finally wrap up with some hopefully enlightening conclusions. I think we can all sort of agree that every new vehicle will be connected. Users' expectations are being lifted up by adjacent industries, by consumer electronics, smartphones, IoT. Users are expecting more and more. And the industry pioneers, which were mentioned earlier, are really kind of leading the way and again, raising people's expectations about what a connected vehicle should be. We all know that connectivity is a requirement in many regions of the world now, and through the move to electrification of vehicles, the vehicle platforms themselves are becoming somewhat commoditized. So actually the user's experience of the vehicle, both in the vehicle, their tactile experience and driving experience, but also outside the vehicle, where they're spending 23 plus hours a day, is becoming more and more important with electrification. Running kind of in conflict to that then is, if there is lots of opportunity out there, there is also a lot of challenge coming in. So we've already heard a bit about system complexity increasing, so with the move to domain and zonal architectures, software complexity is increasing, and also supply chain complexity is increasing, because previously you could buy a box off a shelf and put it in a car. Now you're actually having to consolidate multiple products from different vendors and get them all to play together in the same space and not interfere with each other. So you've got lots of complexity coming in, and out in the wild more vulnerabilities are being found in software. And that's probably a good proxy for the fact that there are more people looking, but also there are more vulnerabilities in more complex software generally. And add to that the geopolitical tensions. A global OEM is a great target if you want to hit a high-profile company. That triangle is flatter than it should have been. It's meant to be an equilateral triangle. So this is the sort of classic triad that we see in cybersecurity. It's the trade-offs between security, functionality, and usability. And if you wanted to think about Apple and where they put iOS, they don't focus on having all the bells and whistles and every bit of functionality. They focus on high security, and they focus on high usability. Android, on the flip side, does try to be all things to all people, and they focus perhaps more on the functionality than on the usability. There's a trade-off between those three things. The functionality, you're pulled by the market dynamics, by the market saying, I want this feature, I want that feature. Security is baselined by compliance. You've got to have some cybersecurity to get compliance in given regions. But it's probably more pulled by reliability and brand. If you want to be seen as a reliable brand, you want to be seen as a secure brand, then you tend to focus more on the security side. And I think the usability kind of pull is really by satisfying your customers, getting repeat purchases, and people enjoying the products that they're buying. And performance is a massive part of usability, arguably the most important part. When you read reviews of mobile apps for vehicles, the thing that is usually complained about is resiliency of the connection and the performance of it. Having to wait for the screen buffering is one of the major concerns. So I want to introduce the concept, which I'm sure you've heard before, of the performance penalty. So people talk a lot about, adding a security mechanism adds a performance penalty, and there are quite a few, high-profile security features that have been added to, computers, smartphones, the internet, which have brought with them an associated performance penalty. But it gets to the point where the market and the industry accept that penalty because it becomes the de facto standard thing to do. An interesting one is perhaps the last one of those, SSL. Back in the 2000s, every internet connection wasn't encrypted. Everything was done over clear text, pretty much except login pages when passwords were sent, and some high kind of end banking transactions. But most things were just done over HTTP clear text. At some point, the world decided that this wasn't acceptable. As eavesdropping and spoofing of data became more prevalent, and at the time, when in 2005, when Intel did a report, they looked at the performance overhead of adding SSL to every connection, and it was thought to be about 70% of a web server's performance power going into that. These days it's under 1%, and that's because the solution's been optimized in software, so it's less of an overhead, and then it gets moved into hardware. As it becomes such a dominant workload, it's worth investing the time to have a hardware accelerated solution for that. And now we take it for granted. So if that's performance penalties, can we have both our cake and eat it when it comes to connected vehicle solutions? First of all, I want to talk about performance of connected vehicles, because there isn't one measure where you can compare different OEMs and say this solution is faster than this solution. So at Beam, we've sort of standardized into two sort of messaging patterns. One is telemetry, which is a one-way flow of data from the vehicle up to the cloud and onto a mobile app. The second is a remote command. So this is a user-initiated action, perhaps unlock my doors or send a navigation location to my car. And that's a round trip from a phone through the cloud down to the vehicle and back to the phone. And we can measure both of these, come up with kind of objective measurements, and benchmark a solution against another one. The latter of those two is actually a bit easier to measure because the start point and stop point are on the same device. It's the same clock on the same phone, so it's very easy to measure the timing for that. The first one is more difficult as you've got two different clocks where it started and stopped, and you need to make sure they're synchronized to make sure your start time and your stop time are kind of level. So looking at round trips, we sort of designed a methodology and some tooling around performing thousands of iterations of a ping to a vehicle. So that is just sending a command that says hello and then getting a response back from the car. We took that to Millbrook last year, and we used their private cellular network, and that's really important because it takes one of the variables out of the exchange. You know that there isn't other contention or traffic on the mobile network because it's a completely private network that you're using. So we controlled a number of those test parameters, ran thousands of iterations with different configurations to understand what the security, the performance penalty was of different security mechanisms. Now, these are the three test scenarios that we ran, but first of all, I guess I want to talk about underlying security. So for all of these cases, we kind of established a baseline set of security that you need. You can't do a connected vehicle without encrypting all the point-to-point connections. So that is the phone to the cloud and the cloud to the car. Each of those tunnels, if you like, is an encrypted tunnel using TLS. And similarly, each point-to-point connection is strongly authenticated at both ends using certificates, X509 certificates. So that's your underlying security controls. And then we ran these three different test cases. The first one being no payload protection. So, and maybe that sounds scary, but actually that's what most people do today. It's kind of accepted. So that's the bronze solution in my case. And that's where you send a clear text message through those two encrypted tunnels down to the vehicle and get a response back. The second case that we timed then was, what if you use elliptic curve digital signatures and cryptographically sign those messages at both ends when you receive it and then when you send it back, and implement that in software. The third case we looked at, which is like the gold standard, if you like, is having secure hardware at both ends, so on the phone and on the TCU, the telematics unit in the car, and then doing the cryptography in a hardware accelerated module and storing the keys in secure hardware so they can't be extracted. So the graph. It's quite a kind of high-level summary here, but what you can really see is that the second test case added about 24% overhead to that round-trip ping command, and the third case, as you would expect, is a bit quicker because you're moving that performance penalty from software into hardware. So it sort of reduces to 11%. Now, of course, this this test is on a ping command, which is a kind of rather academic example, right? There's no real value in pinging a car. So it's a very quick turnaround at the car, and there's no kind of overhead of processing time at the car other than turning the message around. So if you start to think about including the vehicle network time, the ECU processing time, and perhaps the handshakes that go on in the vehicle for any given command, you can add on an additional amount of time to think about the specific command you're running this for. So you can see at the bottom here that if you add on 423 milliseconds, which is the average time it takes with one of our OEM customers to action all of the doors, you can see that performance overhead reduces to 4%. So it's becoming like negligible as you actually start to do useful things in the vehicle. I think the other sort of takeaway there is that this is a highly performant, like optimized platform for doing this. In the majority of connected vehicle platforms out there, the 304 milliseconds can be doubled, tripled, 10 times that. So actually the performance overhead for a less performant platform is much, much smaller. Right, so to wrap up, that's the kind of technical bit done. So, in closing, I guess I would say that the performance versus security trade-off can be demonstrated, and moreover, the data can be captured, and it doesn't need to be a gut feeling or a finger in the air decision about whether you implement a security control or not. You can measure it and make a data-driven decision about whether it's worthwhile. I think also the decision about whether to put any given security control in place, and I've shown you an example, but of course, there are loads of different controls you could put in there, is really a function of a few things. The brand and where you want to position yourself, in the market. Are you highly secure? Are you all the functionality, or are you highly usable? The threat model, because of course, the people looking to attack a autonomous mining truck is very different to the people looking to attack a Ferrari in central London. So the threat model of the vehicle also dictates which way you go on that decision, and the time criticality as well, because there are some messages that are highly time critical. So perhaps I want to unlock my doors. I'm standing there. I'm waiting. It's raining. That's probably more time critical than I want to send a navigation location to my car because I want it to be there when I walk out and step in. So the time criticality can also govern whether you implement a security control or not. And so I guess in closing, we think you can have high security and high performance, but it's what that means to you which is important in your position. So the last bit, if we look at the other examples of the performance penalty that I showed earlier in the wider tech industry, I think there were two things that you could see. One is that the climate is going to keep getting increasingly challenging. Things aren't going to get easier; they're going to get more difficult. And also, we saw in a number of cases that the performance penalty reduces as the solutions and approaches to solving these problems mature. So as those solutions get optimized in software and eventually move to hardware, the performance penalty will reduce. So you can't just take a snapshot view of today, what do I think I should do? You need to kind of reevaluate that as things change, because the cyber climate keeps changing as well. So that's my main closing remark, although in the words of Colombo, there is one more thing, and that is AutoCherry is a project that we've recently started with some consortium partners. It's a UKRI funded project looking into the performance and security, funnily enough, trade-off of Cherry, which is like a chip-level innovation from University of Cambridge and DARPA and a number of other organizations. And it's implemented in an ARM processor, which we're using as our kind of development board. So we're looking into this over the next probably 20 months now, maybe 18 months, and hopefully we can give you an update on that next year, or if you follow our website, we'll be posting updates there. So that's it. Thank you.